will recall, well you won't, but you'll be reminded that if we write the time-independent Schrodinger equation in spherical coordinates, that it generically looks like this lovely monstrosity. So there's the radial piece, or the radial operator there, and then you have the angular piece, minus h bar squared over 2mr squared, 1 over sine theta, partial with respect to theta, of sine theta, partial with respect to theta, plus 1 over sine squared theta, second partial with respect to phi, plus some potential. We're assuming spherical symmetry, so that the potential only depends on r and not on theta and phi. All of that entire Hamiltonian operator applied to the wave function as a function of r, theta, and phi, the spherical coordinates, all of that should be the energy times psi of r, theta, and phi. That's our time-independent Schrodinger equation. Isn't that beautiful?
PHYS Shrek, yes.
Yes, time-independent Shrek, as a matter of fact. And this piece here is L squared over 2m r squared, where L squared is the total angular momentum squared operator. We said the angular piece is L squared, the L squared operator, and since it's multiplied by the 8 by 1 over 2m r squared here, minus h bar squared times all that in brackets is L squared. So minus h bar squared over 2m r squared times all that in brackets is L squared over 2m r squared. And we have already effected a separation of variables. So we already know that the eigenfunctions of L squared are the now if I had been speaking more clearly when I said I would have said what? Spherical harmonics are the spherical harmonics. Oh, I'm sorry, I said that incorrectly. The spherical harmonics YLM of theta and phi with the L squared operator applied to YLM of theta and phi gives back eigenvalue minus h bar squared LL plus 1, not minus h bar squared, just L plus 1, no minus, h bar squared times YLM of theta and phi. If I hit YLM with L squared, I get LL plus 1 h bar squared back times the YLM. So the eigenvalues of L squared are LL plus 1 h bar squared, where L can be 0, or 1, or 2, or 3, or 4, or 5. 1 million years later, he would say, or 74,650,000,000, no, any integer. Note that we have not yet constrained the energy. We've constrained the angular momentum. We know that the angular momentum can only take on certain values, but we have not yet constrained the energy. Ooh, that's the fun part. No, the whole thing's the fun part. Even more fun is coming. Note that we have not yet constrained the energy, so this must come from the radial part of the wave function.
says we already that.
Oh,
Yeah,
yeah, we already that.
yes, no, yeah.
We already know that, yes, as a matter of fact. So what we're going to do is look for solutions of the form that psi, and we'll label it with ELM of our theta and phi. So in other words, we're looking for wave functions which are eigenfunctions of L squared and also LZ. Remember that we can find simultaneous eigenfunctions of L squared and LZ. So the quantum number associated with L squared is L, the quantum number associated with LZ is M, and we also want to be able to find energy. So we're looking for wave functions, in other words, that simultaneously have well-defined values of the energy, the angular momentum squared, and the z component of the angular momentum. And those will factor then into some radial function, capital R, ELM of R, times a spherical harmonic, YLM of theta and phi. And this is all perfectly generic. We haven't said anything about what V of R looks like. We're going to make V of R the hydrogen V of R, but in the book you'll see details of a solution for, well, what about the spherical box, as it were? In other words, you've got a particle that has to live inside some hollow sphere. It's not allowed to go outside of it. And you can solve for what the radial part of the wave function looks like in that case. We're going to concentrate on what happens for hydrogen, but whenever you've got a spherically symmetric potential, where V only depends on R and not on the angular variables, then the wave function solutions of the time-independent Schrodinger equation have this factorization. And different potentials lead to different capital R's, but they all have in common that the angular dependence is still YLM. Okay, any questions at this point? So, V plug and V chug. Pluggeth and chuggeth after, okay, I'll get this too. After substitutingeth into our buddy Shrek there, the time independent. Substitutingeth, it's not a word, I'm just making S on the end. After substituting into the time independent Shrek. Yeah, I'm being like old English tiny here.
No, it should be substitute it.
So after, okay, oh, you want me to substitute it?
Yeah, and then.
Okay, how about, okay, if you like, substituteth, pluggeth, and chuggeth. All right. We obtaineth. Okay. Minus h bar squared over 2m, 1 over r squared ddr of r squared ddr, plus, so these are becoming total derivatives here because of the fact that they're only operating on this function r that only contains the radial variable, plus, and then when I smack my separated wave function in, the angular part, L squared over 2mr squared applied to the YLM is going to pick out L plus 1 h bar squared. So we'll get L plus 1 h bar squared over 2mr squared plus V of R. All of that smacking into REL, in principle, M of R YLM of theta and phi equals E RDL M of R YLM of theta and phi. Now actually, the M subscript is not needed because, well, can you guess why don't we actually need an M subscript there? I'm going to argue that actually the radial function can't depend on the value of M. It's not that it's on the xy plane. Is there anything special about the z-axis? Is there any magical direction in space that's the z-axis? No. So there's nothing to tell us what directions make the z-axis. Hmm? No, it's just because if v only depends on r, there's nothing to pick out a special direction called the z-axis. It's just up to us what we call the x, y, and z axes. So in other words, the value of the angular momentum with respect to some particular axis can't affect the solution, it turns out. Now, I don't want to dwell too long on that, but basically we don't need the M subscript. We will see directly that in general R doesn't have any dependence on what M is equal to. And it's essentially because I could have picked any direction to call the z-axis. And so it turns out that that's not important. The energies are independent of M, it turns out. The z-axis direction is arbitrary, so the energy can't depend on some arbitrary choice of z-axis direction. So E cannot depend on this choice. E can't depend on that choice, so really we only need R and L, we can call it. We don't have to worry about M. So from this point on, I'm just going to say R and L. And so now, after I've already applied the angular piece here, the angular operator, and gotten a number back because the YLM is an eigenfunction of it, now notice that I am free to cancel YLM on both sides. Because what does this operator think the YLM is as far as it's concerned? It's effectively a constant because these are derivatives with respect to R. So it just doesn't, the YLM can come out of this operator. It can go out to the front of that operator. And this is just a constant, and this is not a constant, but it's just a function of R. So in other words, after we've already applied L squared and gotten back the eigenvalue, now the angular dependence just factors out. I could pull this out to the front over here and only apply the operator to R, and obviously here this is just E times the R function, and so then we can just cancel the angular dependence on both sides. The YLMs cancel, and so now we've got something that only depends on R. Yes?
So how come there be any case that there is a the derivatives inside of B, right? Like B would be something B over dr?
No, because the potential here is just a function of the position coordinates. And so if we're sitting in the coordinate basis, it's only going to be a function of R theta and phi. Yeah, it'll be, well, we're making the special condition that there's spherical symmetry, so it only depends on R. In principle, you could have one that depends on theta and phi as well, but it's never going to depend on their derivatives because it's just the potential energy as a function of position. So in the position basis, it's only a function of the coordinates, not of their derivatives. Yeah. So this really is, even if this were, now if this were V of R theta phi, things would be different here because we would spherical symmetry, so we get to make that cancellation. And so that means now we've got something which only has r's in it. It's an equation only for the radial part of the wave function. It contains something that came from the angular part, but determining the radial part of the wave function, while it contains that eigenvalue in it, it's still just an equation that only has r in it at this point. So we've got a differential equation that is an ordinary differential equation with r as the independent variable.
Don't you think that it's kind of confusing to people because that m to mr squared is like mass x squared?
Yeah,
And
correct.
x cubed is the-
Correct. So go slap the early pioneers of quantum theory around a little bit for using m as the, yeah. You're right. You're right. Which is why sometimes we'll put like this is like m sub l to indicate that it's the orbital z component of angular momentum quantum number. But yeah, you're absolutely right. We're using exactly the same symbol, and I'm just going to rely on realizing that when it's down here, it means the mass, and when it's here, it means the angular momentum z component quantum number. So shoot them, but not me, because I'm just doing what they did.
Yeah.
All right.
Never shoot the messenger.
Yeah. Now, we are going to change variables. Define UEL as a function of r via the radial wave function REL, by definition, is UEL divided by r. So in other words, equivalently, UEL is little r times big R EL. But that's how we're going to write it. So the radial piece of the wave function, by definition, is UEL over r. Wait, is it because I keep saying UE? Is that what you're... okay. Well, so this is great, right? Because now we've got spiritual harmonics, and there's UEL and all that, so it's like, whatever. Anyway, then 1 over r squared ddr of r squared ddr of REL. In other words, what we've got over here for the radial piece, all that, let's rewrite that in terms of UEL. That's equal to 1 over r squared ddr of r squared ddr of UEL over r equals 1 over r squared ddr of r squared, and then if I differentiate UEL over r, what do I get? What's the derivative of UEL over r? Symbolically, I mean, we don't know what UEL is as a function of r yet, so symbolically, what is the derivative of UEL over r? Plus 1 over r duel dr. I should just use the product rule on it. So we get that that is 1 over r duel dr minus UEL over r squared, just using the product rule. So now I'm going to multiply through the parentheses by r squared and take the derivative of that. So this becomes then 1 over r squared ddr of the quantity r squared times 1 over r gives me r duel dr minus, and now I've got r squared over r squared, so we just get minus UEL. So now I have to take the derivative of r du dr minus uel. So now I get 1 over r squared. Okay, when I take the derivative of r du dr, what do I get? Right, r second derivative of uel plus just du dr, because you take the r derivative of r, you get 1, and then minus du dr, and then you start to see why we did this, because we're going to get a cancellation here. So we get 1 over r squared du el dr plus r d squared u el dr squared minus du el dr. So those first derivatives cancel one another, which is why we bothered to do this. So then in the end, we just get 1 over r times d squared u el dr squared. So making that substitution considerably simplifies this piece right here compared to if we don't make that substitution. For some reason I keep wanting to say ties today instead of Shrek. So Shrek or ties, take your pick, becomes minus h bar squared over 2mr times d squared uel dr squared, that's from the first piece, plus l plus 1 h bar squared over 2mr squared times uel over r, because it's rel, but that's uel over r, so the second term I have to plug into uel over r, plus v is a function of r times uel over r is equal to e times uel over r. So everywhere in the other terms that I didn't work with yet, I've substituted uel over r wherever there was rel before. And so then we've noticed that, oh look, I can clear those 1 over r's that are common to every term in there. I can just multiply through by r to clear these 1 over r's that are hanging out everywhere. Or minus h bar squared over 2m d squared dr squared as an operator. So I'm going to put square brackets around and make an operator that smacks uel, plus l plus 1 h bar squared over 2mr squared, plus v of r, all that hits uel and gives back e times uel. And the thing to notice about this is, well, what does the one-dimensional Schrodinger equation look like? If we had x as the variable and we were in one dimension, the 1D, suddenly I'm back to Shrek again. 1D Shrek says minus h bar squared over 2m d squared psi dx squared plus v psi equals e psi, right? That's the one-dimensional Schrodinger equation. Look at what we have here. It looks exactly like it with what we call an effective potential, v of r plus l plus 1 h bar squared over 2mr squared. we have here is a one-dimensional Schrodinger equation where r is the variable, and what's playing the role of the potential is not v of r, but v of r plus L plus 1 h bar squared over 2 mr squared. So in other words, we've reduced our problem into the one-dimensional Schrodinger equation. Hoo-ha! So that's the real payoff here of introducing UEL here, is that in terms of UEL, you get back to one-dimensional Schrodinger equation. Now again, implicit is the angular piece has produced this L plus 1 h bar squared over 2 mr squared term. But once you know, once you throw in the YLM and throw in its eigenvalue, the radial part of the Schrodinger equation, the radial piece just becomes a one-dimensional Schrodinger equation with this effective potential. Now, there's another difference here. In general, x in the one-dimensional Schrodinger equation ranges between what and what? X here, in general, varies between what two values? Minus infinity and plus infinity, right? What about r here? It's varying between what two values? 0 and infinity. Because you can't, because the origin is r equals 0, and you can't go to negative r, right? So r goes from 0 to infinity here, instead of from minus infinity to infinity. But that's essentially kind of saying, remember there was a question on the exam where the potential went to infinity at x equals 0. And then, I said, what if you had a potential that looked like that? Like the half-infinite square well. This is not a square well, but it's similar in that you can say, well, the potential goes to infinity at r equals 0, so that the particle can't get past r equals 0 into negative r. That's effectively what you've done here. And you've also done it by saying, look, there's a 1 over r squared there, so this blows up as you approach the origin. So in fact, let's sketch VEF, the effective potential, as a function of r. So, it's going to depend on the details of what V of r looks like, but kind of generically speaking, we get something which looks like this. Or at least we certainly can. So if this is the r-axis here, and then this is the effective potential as a function of r, then depending on the form of V of r, you can make V of r such that it's blowing up too, but assume that L plus 1 over 2 mr squared dominates for small values of r, then the L plus 1 over 2 mr squared blows up. It looks like 1 over r squared, which blows up as you approach the origin. We refer to that as the centrifugal barrier. In other words, it tends to keep the particle away from the origin because the potential is getting large there, and the wave function tends to be small for a given energy when the potential is getting large. What if we just suppose that this is the energy? And let's suppose that V of r goes to 0 as r goes to infinity. Then we'll have that V and VEF go to 0 as r goes to infinity. So kind of generically, the effective potential will typically look something like this. And then in between these 2 points along the axis, in between these 2 points, the energy is greater than the effective potential. So go back to the Schrodinger equation, minus h bar squared over 2m d squared u dr squared plus v effective u equals EU. We're in a region where the energy is greater than the potential energy. Does that make the wave function tricky or XP? Go back to the one-dimensional Schrodinger equation days. Is that the tricky or XP case? That's the tricky case. That's the tricky case. UEL is tricky there. It won't just be a simple sine or cosine or e to the IKR type of thing because of the fact that the amount by which it's greater is changing, right? It's a simple e to the IKX type of thing if the potential is a constant, if E minus D is a constant. But in general, it's going to be tricky. It's going to be oscillating in this region. And then over here, E is less than def. So UEL is XP. And over here too. So we're going to have the usual situation where boundary conditions are going to constrain us. We're going to want the wave function not to blow up as r goes to infinity. That won't happen for arbitrary energies, but for certain special energies it will. And we're going to want the wave function not to blow up at the origin either. That won't happen for just any old energy, but for certain special energies it will. Those special energies will depend on the potential, depend on the form of V of R. If the V of R happens to be hydrogen, I'm guessing the special energies are going to look like something like minus 13.6 electron volts over n squared, where n is an integer starting with 1, 2, 3, 4, and that's exactly what we're going to find out, is that for the Coulomb potential, the energies are minus some constant over n squared. Just like you've seen in the past, but now we're going to derive that fact. So, any questions? So that's generically what we're dealing with here. And now, let me find where I want to be here. Okay, let's see. And no, not you. Skipping some things, going to here. Yeah, general properties of UEL. General properties of UEL. Well, one is she whines a lot.
That's cool. That's
That's
like
more.
my specialty.
Yeah, that's right. But more important, let's look at our spec here. So, minus h bar squared over 2m d squared UEL dr squared plus v of r plus L plus 1 h bar squared over 2mr squared. And then let's pull the energy term over to the other side. UEL equals 0. So we just pulled the energy piece over to the left-hand side and made the whole thing equal to 0. And then what we'll do is we'll look at the behavior of this stuff inside the square brackets for small r and for large r. If v of r is less singular, so to speak, than r to the minus 2, as r approaches 0, in other words, if it blows up more slowly than 1 over r squared does. So for example, you know, we're dealing with hydrogen, so we're going to be especially interested in the Coulomb potential. So in hydrogen, the Coulomb potential is minus e squared over 4 pi epsilon naught, what power of r? If I have a proton and an electron attracting one another, they're a distance r from each other, the potential energy is minus charge 1 times charge, well, it's charge 1 times charge 2. The proton has charge of e, the positive magnitude of the charge in the electron. The electron has charge of minus e. So charge 1, charge 2 is minus e times plus e, or minus e squared over 4 pi epsilon naught, what? R, just plain r. If I was looking for the force, it would be r squared, but the potential energy is just 1 over r. So in the hydrogen atom, the Coulomb potential for hydrogen is minus e squared over 4 pi epsilon naught r. And r to the minus 1 blows up slower than r to the minus 2. So that's an example of what I mean. In other words, v is blowing up as r goes to 0, but 1 over r squared blows up faster than 1 over r does. So for very small r, this term is a lot bigger in magnitude than this term. The centrifugal term is a lot bigger in magnitude than the v of r term, because for very small r, 1 over r squared is a lot bigger than 1 over r is. Does that make sense? For very small r, 1 over r squared is a lot bigger than 1 over r is. So, you know, if in special unitless units, if r is 10 to the minus 3, then 1 over r is 1,000, and 1 over r squared is 1,000,000, and 1,000,000 is a lot bigger than 1,000 is. So 1 over r squared wins the race in the case of the Coulomb potential to blow up as r goes to infinity. So that's what I mean by v of r is less singular than r to the minus 2. If v of r was 1 over r cubed, oh, it's going to win, and what I'm about to say wouldn't apply. If blah, 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 the centrifugal barrier dominates, the term in parentheses. In other words, E is just some number, so it's not doing anything as R changes. E is just a number. V of R is blowing up as R goes to 0, but LL plus 1h bar squared over 2mr squared, that's really, really blowing up as R goes to 0. So for very small r, you can approximately throw away V, throw away E, and just have this piece at very small r. So we can say that d squared UEL dr squared is approximately L times L plus 1 over r squared times, actually I'm just going to say UL here, times UL. So I drop the E because of the fact that E is becoming negligible. The contribution of E here is becoming negligible, so the result I'm giving here is not going to depend on E, because I'm neglecting E here. I'm saying the only thing that's really going to matter is L for very small r. Drop the E subscript because we can ignore it in this approximation. In other words, what I'm saying is all the wave functions for all the different energies have the same dependence. The E doesn't really matter here. So in this limit, it becomes minus h bar squared for very small r, minus h bar squared over 2m d squared ul dr squared, plus L plus 1 h bar squared ul over 2m r squared is equal to 0. So then what I do is I just take it over to the other side, and now I've got a minus here. When I take this to the other side, I've got a minus there. So those cancel. That's why there's no minuses anymore. And then there's a common factor of h bar squared, which I simply canceled, and a common factor of 2m, which I simply canceled. So the equation just becomes d squared u sub L dr squared is approximately L plus 1 over r squared ul as r approaches 0. So that solving that equation gives us an approximation to what ul looks like for small r, what the u looks like for small r. So can anybody just look at that and tell me what u is? I can't. But this is one of these deals where, okay, well, I don't know what the answer is, but let's just try to guess. Let's just assume that ul goes like r to some power of alpha. Can I just solve it with r to the alpha for some value of alpha? So if I do that, then what's the second derivative of ul with respect to r? If u is r to the alpha, what's the first derivative? Yeah, alpha r to the alpha minus 1. What's the second derivative? Right, alpha minus 1, r to the alpha minus 2. That's the second derivative of r to the alpha. So if we plug our proposed solution into this approximate differential equation for small r, we get alpha minus 1, r to the alpha minus 2 should equal L plus 1. Oh, look. What's r to the alpha over r squared? R to the alpha minus 2. Hey, it worked. It worked. So in other words, so we want alpha times alpha minus 1 to equal L plus 1. And it's easy to convince yourself that'll happen if alpha is equal to L plus 1 or alpha is equal to minus L. Either way it works, because if alpha is L plus 1, this becomes L plus 1 times L. Right? If alpha is L plus 1, this becomes, the alpha is L plus 1, alpha minus 1 is L, so this becomes L plus 1 times L. Is that equal to L times L plus 1? Typically, right? So that would work. Or, if I put alpha is equal to minus L, this becomes minus L times minus L minus 1. Is minus L times minus L minus 1 equal to L times L plus 1? Yep, it is. Yeah, because you just got a factor of minus 1 you can pull out of both terms. So either of these will work. Either alpha is L plus 1 or alpha is minus L. That'll give you a solution. Und so, wir haben UL ist egal mit r to the L plus 1 or r to the minus L. Either one of those will work. So that would be what we call the regular solution. This is the one that needs to go to the drugstore. That's the irregular solution. Now, anybody see a potential problem with the irregular solution as r goes to 0?
Yes.
Kaboom! Right? The irregular solution blows up as r goes to 0, so we reject it. Well, actually, that's not why. It is because H will not be permission if we use that solution. But even your book just kind of says, we're going to reject it because it blows up. Well, that's not really why. It's because, and it doesn't even say what the problem is, but it makes a reference to Shankar's book, which is the one that I used as my reference for talking about Dirac notation and so forth. In Shankar's book, you can see the derivation that if you demand that the operator be Hermitian, you find that the boundary term doesn't go away if you try to use the irregular solution. And that's the real reason why we have to reject it. But we can hand wave and kind of say, yeah, but it blows up and that doesn't look too good, does it? And so it turns out that even though that's not quite a good enough justification, it still works out to be that you have to throw away the irregular solution. You don't want U to blow up. And essentially, it's that blowing up that screws up the hermiticity. The boundary term would have r equals 0 and r equals infinity, and the boundary term isn't going to go away if U blows up to infinity, and that's the real problem there. It makes the it makes the operator not permission if you allow those wave functions in. So you don't allow them in. They're not even on the border of our space of functions, and so we do not invite them in. We put up barbed wire and say, out, out, none of that. So, time for a break. So let's have a break, shall we? What? You don't want a break? You want to get... Oh,